Welcome back to our course ME22088 Vibration and Noise Control. We are now in fifth unit, section 7, where we will be focusing on experimental model analysis. This is the practical aspect of understanding how structures vibrate through experimental techniques. Today, I am starting with the crucial important topic signal analysis in the context of experimental model analysis. Understanding the characteristics of the signals we can occur fundamental and accurate properties of the system through model parameters. I am Sandamare Kannan, Associate Professor in the Department of Mechanical Engineering at SCC. Let's begin our journey into the world of signal analysis and lay the groundwork for understanding how we can extract valuable model information from measured vibration data. Let's talk about digital signal processing, which is a fundamental aspect of how we analyze the signals we occur through experimental model analysis. In this real world, the vibration we measure from a structure are continuous signals that vary with respect to time. We call this as analog signals represented as x of t. However, our analyzers and computers operate in the digital domain, meaning they work with discrete numerical values sampled at specific time. Therefore, first crucial step is to convert these continuous analog signals into digital signals or digital records represented as xi equal to x of ti, or it may be xn, or it may be x of j in the subsequent plots. Let's look at the top row first. On the left, we see a simple analog signal x of t, which appears to be a sinusoidal wave. This represents a continuous vibration over a period of time. In the middle, we see the corresponding digital record represented in the frequency domain. Omega 1 is a frequency domain versus x of n. Notice that instead of a continuous spectrum, we now have discrete spectral line at specific frequencies, omega 1 and omega n. This is result of the sampling process and subsequent Fourier analysis. For a pure sine wave, we would expect to see a single dominant peak at its frequency. On the right, in the top, we have another representation of the digital record x of j versus t of j. It is time with respect to j. This shows sampled values of the original analog signal at discrete points. The density of these points depends on the sampling rate what we choose during data acquisition. Now we go to the second row of these representations. Here the analog signal x of t is a complex waveform. It is not simple, appearing as a sawtooth wave. This represents a vibration with multiple frequency components. The corresponding digital record in the frequency domain shows multiple spectral lines at different frequencies like omega 1, omega 2, omega 3, omega 4, so on up to omega n. The height of each line represents amplitude of that particular frequency component in the digital signal. This illustrates how complex vibration signal is composed of multiple sinusoidal components at different frequencies. Similar to that, the plot on the extreme right of the second row shows sampled values of the sawtooth analog signal at discrete time points. Again, the digital record is a series of discrete values that approximate the original continuous signal. To summarize, we are essentially taking continuous analog signals from our transducers and convert them into series of discrete values. We then use digital signal processing techniques, particularly fast Fourier transform analyzer, to analyze the frequency content of these digital records. This allows us to identify the natural frequencies and other model parameters of the structure from the frequency spectra what we obtained. Let me discuss somewhat depth in digital signal processing. The mathematical foundation began how digital analyzer decomposes discrete time domain signal into its frequency components using a form of the discrete Fourier transform. As we saw, our analyzers take a series of discrete data points x of j which represent our sampled analog signal. This slide shows one way these discrete values can be expressed as a sum of sinusoidal components. The first equation here represents finite Fourier series approximation of our digital signal x of j at discrete points. Let's break down the equation. This equation, what it implies, x of j is the amplitude of the digital signal at the jth time sample, that is at t of j. A naught by 2 represents the DC component of the signal, otherwise average value of the signal. Summation represents series of cosine and sine waves with different frequencies. The frequencies of the sinusoidal components are given by T of I, which is ranges from 1 to n by 2, where T is the total time duration of our sample record. AI, BI are the coefficients that determine the amplitude and phase of each cosine and sine component respectively. Here we are having another formula to calculate these coefficients from our digital data. That is, this confirms AO is indeed related to the average value of the n data points. Here, this equation shows the AI associated with the cosine terms. We calculated the input signal x of j with cosine waves of different frequencies. Similarly, BI coefficients associated with the sine terms are calculated by correlating the signal xj with the sine waves of different frequencies. Still, we are simplifying the representation using matrix rotation. It is in matrix form. Here, it is the notation for matrix form, that is A inverse into X, where X is nothing but vector containing n number of sample data points and D vector containing calculated Fourier constants. In that, matrix A would be containing the cosine and sine basic functions evaluated at the discrete points. Here, n is fixed for a given analyzer. This means that the number of discrete data points our analyzer collects in a given time window is determined by its hardware settings, particularly sampling rate. This value of n directly influences number of frequency component we can resolve in our analysis. So in essence, this equations shows the mathematical process by which our analyzers takes a time domain vibration signal, discretizes it into a series of data points, and decomposes it into a sum of individual sine and cosine waves at different frequencies.
In an ideal world, our measured input forces and output vibrations would be perfectly clean signals. However, in reality, our data invariably contains some level of random noises. This noise can originate from various sources such as electrical interference in our measurement system or inherent randomness in the vibration itself. The graph at this slide shows a typical random signal x of t which is plotted against time. You can see that it is not a clean sine wave or simple periodic signal. It exhibits irregular, unpredictable fluctuations superimposed on any underlying periodic components. Given that random signals fluctuate unpredictably, a key parameter for characterizing them is their average value. The slide provides the definition of the average of a continuous random signal x of t as x of t, it is t with respect to limit tends to infinity integration of x of t dt. This equation tells us that the average value is obtained by integrating the signal over a very long period, that is t approaching infinity, and then dividing by that time period. Essentially, it is the long term mean of the signal. Since our analyzer work with discrete digital signals, we need a way to calculate average in the digital domain. So, how to calculate the average? This is the equation for that. Here, we sum up very large number n approaching infinity, n to infinity, of the discrete sampled values x of j and then divide by the local number of samples itself. This gives us the digital equivalent of the long term average. Why this calculation? The average importance dealing with noisy signals, because the random noise components tend to have a mean value of 0 over a long period. By averaging our measured signals over time or over multiple measurements, we can significantly reduce the influence of random noise and get a better estimate of the underlying deterministic signal components such as structural vibration that we are interested in. Alright, continuing our discussion on the analysis of random signal, this here introducing our concept of the mean square value and root mean square value, which are important for quantifying the power or intensity of a fluctuating signal. To analyze the fluctuating part of a random signal, it is often useful to remove its average value first. The slide, we are starting it by defining a new variable x of t as the original signal y of t minus its mean value. That's why we are putting bar here. This effectively centers the signal around 0, allowing us to focus on the variation of the AC component of the signal. Now, to quantify the power or intensity of this fluctuating signal, we use the mean square value continuous signal. Essentially, we are taking square of the signal at each point in time, integrating this sequenced value over a long duration t and dividing it by once again t itself. Squaring the signal that both positive and negative fluctuation contribute positivity to this average power measure value. Our digital signals, the mean square value x of 2 is calculated similarly by averaging squares of the discrete sample over a large number of samples. While the root mean square value gives us a measure of the signal's power, it's often more convenient to work with a value that the same units as the original signal. This is where the root mean square value comes in. Alright, let's delve into another important tool for analyzing random signals in the context of experimental model analysis. When dealing with random signals, we are often interested in understanding how the signal at one point in time is related to its value at a later point in time. The autocorrelation function provides us with this information. It is essentially measures the correlation of a signal with a time delayed version of itself. So what does the autocorrelation function tell us? If a random signal contains periodic components like a sine wave buried in noise, autocorrelation function will also exhibit periodicity with the same period. This can help us detect hidden periodicity in seemingly random data. What is the strength of randomness? The shape and decay of the autocorrelation function can give us insights into the nature of randomness in the signal. For example, a rapidly decaying autocorrelation function indicates a signal that changes quickly and has a little correlation with its past values, while a slowly decaying function suggests a signal with longer term dependencies. In experimental model analysis, we often focus on frequency domain techniques like FFT. Autocorrelation function can be a valuable tool for analyzing the time domain characteristics also. It can help us to identify periodic components that may be related to structural resonances or external forcing functions. For instance, if you are using random excitation to excite a structure, autocorrelation of the input force should ideally be a sharp spike at zero time lag. Deviation from this ideal can tell us about characteristics of our excitation source. In summary, autocorrelation function is a powerful tool for analyzing temporal dependencies within a random signal, revealing information about its periodicity, nature of randomness, and its power content. It provides complementary perspective to frequency domain analysis in understanding the behavior of the signals what we encounter in experimental model analysis. Let's continue our exploration of random signal analysis, which introduces the concept of power spectral density, cross correlations function, and cross PSD, that is cross power spectral density. These are essential tools for understanding the frequency content and the relationship between different random signals, particularly in the context of input and output in our model testing. We have looked at the autocorrelation function, which tells us about the signal correlation with itself over a period of time. PSD, that is power spectral density, is denoted by SW. Power spectral density essentially tells us how the power of a signal is distributed over a different frequencies. So this power spectral density of a continuous function has the Fourier transform of its autocorrelation function, that is R of t. This equation shows that the power spectral density and the autocorrelation function form a Fourier transform pair. This means that the information contained in one is directly related to the information in another. This S of delta W equal to determinant of x of w square divided by n delta t represents magnitude of the Fourier transform of digital signal of x of t, where n is the number of data points and del of t is the sampling interval. This form essentially estimates the power at each frequency by looking at the squared amplitude of the frequency components obtained from the FFT itself. In model analysis, the power spectral density is incredibly useful for analyzing random excitation signals and resulting random vibration responses. Next, we move on to cross correlation function, While autocorrelation looks at the relationship of signal with itself, cross correlation examines the similarity between two signals like x of t and f of t. If you see the formula here, it is going to taking the signal x at time t and multiplying it by the signal f of time psi plus t, where t is the time lag. We then average this product over a long time period, that is capital T. The result tells us how well the signal x at a given time correlates with the signal f at a time small later. In model analysis, cross correlation function is particularly useful. We have been input and output response also. By calculating the cross correlation, we can identify time delays between the input and output, which can be important for understanding the system dynamics and identifying the cross effect relationship. Further, we move to cross power spectral density. This cross power spectral density is similar to PSD. It is also a frequency domain representation of cross correlation function. This equation of the cross PSD shows that it is a Fourier transform of cross correlation function, that is, which is given above, that is R of x f of psi. The cross power spectral density provides information about frequency content, that is common between two signals, as well as phase relationship between this shared frequency component. In model analysis, the cross power spectral density between the input force and the output acceleration is fundamental for calculating the frequency response functions. So in summary, we are analyzing the random signal in experimental model analysis using power spectral density, which help us to understand power distribution of a single signal across different frequencies, revealing resonant frequencies in the response. Cross correlation function help us understand temporal relationship between two different signals like input and output. Cross PSD help us to understand the frequency content shared between two signals and their phase relationship. Now we shift our focus to see how actually we can extract the model data from the observed peaks in the frequency response function domain. We acquired a data and processed it to obtain this frequency response function. The next crucial step is to identify the model parameters. One straightforward approach, particularly for lightly damped structures where modes were well separated, is to look at the peaks in the magnitude of the FRF. The graph shows a plot of the magnitude of the frequency response function as a function of frequency omega. Notice that there are four distinct peaks: omega 1, omega 2, omega 3, omega 4. Four peaks are suggesting a 4 degrees of freedom system. In general, for a linear system, each natural frequency will correspond to a peak in the magnitude of the FRF. The first step in the peak is to simply identify frequencies at which these peaks are occur. The next step is to identify the damping ratio by using the half power bandwidth method. It is nothing but the peak magnitude is denoted as h of omega 1. To find the damping ratio, we have to look for two frequencies omega 1 and omega 2 on either side of the h of omega 1. So we can drop a vertical line by measuring 0.707 times the peak magnitude. These two frequencies are often referred towards half power points because power dissipated by the system is proportional to the square of the response amplitude. So the damping ratio can be obtained by using this off power bandwidth method. In this slide, we can see the formula what we discussed as a step in the previous slide to calculate the damping ratio. Specifically, we are focusing using the peaks of the frequency response function. By using the frequency response function, essentially by partitioning it into several range of frequency and simplifying it for a single mode, we can able to formalize the off power bandwidth method. That is, because of using that method, we find the width of the resonance peak at a level that is approximately 0.70 times the peak amplitude is the bandwidth that is given as del of omega j. That it is nothing but the difference between omega 2 minus omega 1. That is the bandwidth. The damping ratio is approximately half of the ratio of this bandwidth to the resonant frequency. That is only given in terms of mathematically psi equal to omega 2 minus omega 1 divided by 2 times of omega n, that is natural frequency we can take. Here it is given as omega j. Omega j represents the damped natural frequency itself, and omega n represents undamped natural frequency. For lightly damped systems, the difference between these two is very small. We often ignore it. So, first of all, we have to identify a resonance peak in the magnitude of the FRF. Then we have to find two frequencies, omega 1 and omega 2 on either side of natural frequency. Then we are calculating the damping ratio using the off power bandwidth method formula. Let's look at an example to determine the damping ratio of a system using Bode diagram. Recall that the frequency response of a single degree of freedom system is represented by graph showing how the magnitude and phase angle of its response vary with frequency. Instead of directly working with this magnetic curves, it is often more convenient to use logarithms of this magnitude curves. That is, it is expressed in decibels. When we plot this logarithmic magnitude values and phase angle against frequency, the resulting graph are known as Bode diagrams. In this example, our goal is to find the natural frequency and damping ratio of a system based on its given Bode diagram. Here it is a solution from our example that we can able to find out natural frequency corresponds to the peak of the resonance. In this case, omega n is 10 Hz. To determine damping ratio, we have to use off power bandwidth method. This involves finding the frequency omega 1, omega 2 on either side of the natural frequency, where magnitude of the response is 3 decibels lower than the peak response. The peak response here is 35 decibel. So we look for frequencies which is approximately minus 38 decibel. From the graph, these frequencies are given as 9.6 Hz and 10 Hz. Using the damping ratio formula, we can substitute the value of omega 2 is 10.5, omega 1 as 9.6, then natural frequency itself 10 Hz. Therefore, the damping ratio of the system is 0.045. Let's explore how to determine the model data from a Nyquist plot. For a single degree of freedom system, the Nyquist plot is created by plotting real part of the frequency response function along the horizontal axis and imaginary part along the vertical axis as the frequency varies. The frequency response function denoted here is alpha, can be expressed mathematically in terms of alpha I omega equal to 1 divided by 1 minus r square plus I 2 psi r, where r is the frequency ratio omega by omega n. This complex function can be separated into real parts and imaginary parts in this way, which are then plotted against each other to form the Nyquist plot. Let's see how to estimate the damping ratio from this Nyquist plot. Remember that the plot shows the real and imaginary parts of the system frequency response. Shape of the curve, especially around the point where the frequency ratio R is equal to 1, which is near the natural frequency, which give us information about the damping. The simplified step, first step is identify the point where R equal to 1. On the Nyquist plot, there will be a point which is correspond to the frequency ratio being approximately 1. This point is usually where the curve furthest from the origin or make a sharp turn. Find the diameter of the circle near the point where R equal to 1 by approximately calculating it. The diameter is the straight line distance across this circular path passing through the point where R equal to 1. Measure the distance from the origin to the point where R equal to 1. This straight line is nothing but the distance we are going to measure. Then estimate the damping ratio roughly related to this measurement. A simplified approximation here is, that is, psi equal to 2 times of distance from origin to R equal to 1 point. Alternatively, you can also consider the diameter of the approximate circular path and the distance from the origin to the center of the circle, which is often closer to R equal to 1. However, the basic estimation from the visual plot, the first approximation can give you an idea. Important note for visual estimation, large damping. If a curve around R equal to y is wide, flattened shape and distance from the origin to this region is relatively small, it indicates a large damping ratio. In other words, for a smaller damping, if a curve around 1 is a sharp peak or a tall, narrow curve, the distance from the origin to the peak is very large, it indicates a small damping ratio. The taller and narrower the peak, the smaller the damping ratio. In essence, larger distance from the origin to the resonant region on the Nyquist plot generally corresponds to lower damping. Thank you for watching this video. If you have any further questions or want to delve deeper into specific aspects, kindly email me. I will specifically detail it. Don't hesitate to ask. We will further see it in the next lecture, how to control the vibration. Thank you for your attention.